Hello everyone, I'm Nikhil and I'm going to explain the 5 questions of the assignment part 1 that I completed. So the first question, let me start straight. So the first question was derive the elbow from the KL divergence between approximate posterior and true posterior. Show explicitly how maximizing elbow minimizes this divergence. So I derived the evidence lower bound or elbow starting from the KL divergence between the approximate posterior and the true posterior by applying Bayes' rule and rearranging. We show that maximizing the elbow is equivalent to minimizing KL divergence. This is the cornerstone of variational inference. It gives us a tractable way to approximate the true posterior when it's intractable. In short, the elbow balances reconstructions, accuracy, and regularization, making it central to training models like VAs. So this was the first question that we summarized how we solved it. We'll move on to the second question, that is derive and interpret the analytical KL divergence between two multivariate Gaussian distributions. So this question involves deriving the analytical form of KL divergence between two multivariate Gaussians. So we use the formula which includes the trace, log determinant, and mean difference terms. This result is important in VAs where we compare the approximate posterior and prior, both modeled as Gaussians. The KL term quantifies how far the latent distributions deviates from the prior, and it's used as a regularizer during training. This was the second question. That's how we solved it and derived basically. So we'll move on to this third question, that is discuss the implications of the KL divergence term in the elbow as a regularizer. What happens if it's omitted during training? So to do that, I explain why the KL divergence term in the elbow acts as a regularizer first. It keeps the approximate posterior close to the prior period. If omitted, the model could overfit and encode arbitrary latent representations, leading to poor generalizations. Without the KL term, actually, the latent space becomes unstructured, which defeats the purpose of using VAs for generative modeling. This was how we basically solved the third question and discussed the implications of the KL divergence. And if we'll move on to the fourth question, that is explain mathematically and intuitively why GAN training, that is general adversarial networks, can suffer from mode collapse, and we have to propose solutions and discuss their mathematical reasoning. So in this question, I explored why GANs often suffer from mode collapse, where the generator produces limited or repetitive outputs. This is how basically a GAN collapse. Mathematically, this happens due to non-convex optimization and poor gradients from the discriminator actually. So I also proposed like fixes like feature matching, mini batch discrimination, and using Wasserstein loss to improve gradient flow. These strategies make training more stable and help cover diverse modes in the data. This is how we actually explain the fourth question about why GAN training can suffer from mode collapse. So we will move on to the fifth question, that is explain how a VAE can suffer from posterior collapse, discuss mathematical and practical strategies, like example KL annealing that is written in the question, to address it. So posterior collapse in VAs actually happens when the VA's decoder becomes too powerful and ignores the latent variable Z, so causing the KL term to go to zero. This makes the model act like a plain autoencoder. I explain how KL annealing and using a weaker decoder can help fix the issues. These strategies ensure the model uses the latent space meaningfully and prevents the collapse. So these were the 5 questions of part 1 that we did, and these were the explanation that how I approach the different problems to solve and explain both mathematically and intuitively. Thank you very much. Have a good day.